We have this collision. We're dealing with COM, C-O-M-M. So we've got a conservation momentum component to this. And because we're talking about an object which is converting its kinetic to gravitational, with really no thermal produced after the collision. In the collision, tons of thermal produced, right? All the kinetic energy of this bullet is actually dumped into thermal energy when it collides. But conservation of energy takes over after that point, right? So basically conservation of energy is saying, given an object, given a pendulum which is given an initial push, how high will it rise? So you can see in there's no thermal energy considered. The only thermal energy that might be considered would be due to air resistance, but we're going to ignore that because it's not a significant factor here. Okay, so since we're looking for a variable in the COM model, it stands to reason that we're going to start with COEM, work our way backwards to COM. If, however, we chose to apply COM first, we would find that there was an unknown value, we would go find it, and so on. In fact, let's apply COM first just so we can go through that exercise. Okay, so conservation of momentum says that the momentum before the collision is going to equal the momentum after the collision. It's a completely inelastic collision. So we have mv, where v is the velocity of the bullet. In fact, let's call this object A and B. That makes more sense. So MAVA plus MBVB. That's going to equal momentum of this composite object AB, which exists because the bullet embeds. Don't forget the additional mass of the bullet. It seems insignificant, but in general, if you had a much bigger bullet, then it might be a significant factor. And then we'll just call this V prime. All right. Now the pendulum starts at rest. It's just hanging there. So VB is 0, which means that this whole term goes to 0. So we're allowed to measure this. This is what we're looking for. We know this. We know this. This is unknown. So we need to find this so that we can work our way to find the muzzle velocity, VA, of the bullet. This is where COEM comes in. So conservation of energy says if we define state A, state A is the pendulum after the collision has occurred. It's given an initial kinetic energy. All of the mechanical energy in the system is in the form of kinetic. Assuming conservation of mechanical energy, when it's at its highest point, this displacement of delta H, it's converted all of its kinetic to gravitational. So we can set up our energy equations based on comparing states A to states B. And using A and B is very confusing. They've already used A and B. So we're just going to change it here. We're going to call it this state 1. And this state 2. Go Roman numeral style here. So state 1, state 2 up here. Okay, so then energy at state 1 equals energy at state 2. I don't like the Roman numerals either. Energy at state 1 equals energy at state 2. So kinetic energy at state 1, which is just 1/2 mv1 squared, that's going to equal mg delta H at state 2. Okay, so we see, and I've used mass here to refer to the composite mass. Doesn't matter because it crosses out. So the mass is irrelevant. Given a pendulum that you give a certain push, if you know what the initial speed is, you know the height it's going to go, no matter what the mass is. Okay, so that means that we can solve, we know G, we've got to find this delta H. To find delta H is just a math problem. This is a right angle triangle. This is L. This is a given angle. So you can find delta H by finding what we might call y here. So L extends all the way down. L is the sum of y plus delta H. So you could just find y using trigonometry, because you know this angle, and you know the hypotenuse. And then you can subtract that from L to find delta H. So this is something you've done several times at this point. So delta H is a known value. And you figured out using some geometry. So that means that now you know this quantity, which is the initial velocity of the bob with bullet embedded. Now this is the same as this. That's what links the two models. So now you can work backwards and you can solve. And that will be the muzzle velocity of the bullet.